Hi kids, welcome back. We're going to study two-dimensional collisions now, which is covered in section 5.4 in the textbook. So it's just an extension of what we learned before, where everything was in a line, one-dimensional. And the categories for collisions that we learned about in one-dimensional collisions still exists here. We still have elastic collisions where the kinetic energy and the momentum is conserved. But since it's a two-dimensional situation now, and momentum is a vector, what we need to do is break down the momentum vectors into their components. So not only is momentum conserved in its totality, but momentum is also conserved strictly in the x direction, and momentum is conserved also strictly in the y direction. There's no need to do this breaking down with kinetic energy because kinetic energy is a scalar. We still have inelastic collisions where the kinetic energy is not conserved, but the momentum is conserved still. And that means also conserving totally in the x and totally in the y, and then both together. We have completely inelastic collisions where the kinetic energy after the collision is much less than the kinetic energy before the collision. The objects stick together, but what we learned about momentum being conserved in the components, that is still true. Still true. So look, momentum being conserved is true in all of these situations right here. Now, how do we solve these problems? Well, there's two main methods here. There's the geometry, trigonometry way, say that 5 times fast, which involves things that you know already, like sine law, cosine law, drawing a triangle diagram, doing vector tip to tail addition. That's one way of solving it. Some kids like to use this method when solving two-dimensional collisions. Some questions are easier when using this type of solution. The other type of solution is the component method. We've been using it all course, where we break down all of the momentum vectors into their x components, and we break down all the momentum vectors into the y components, x and y components, and move forward with a set of equations. All right, so we might as well start with one of the sample problems from the textbook. It's on page 254, 255. So uh, take a second to read the question and read through the solution. And so pause the video now, read the question, read the solution, and then we'll come back. All right, so it says a 38 kilogram child, 38 kilogram child, C for child, is standing on a 43 kilogram raft, R for raft, and is drifting with a velocity of 1.1 meters per second north relative to the water. So the child and the raft are moving together. There they are. Here's a picture of the raft and the child, and they're moving together there. The child then, so this would be after. The before situation is the child not walking. The after situation is the child walking. And then how the raft responds, because we have to conserve momentum. This is a type of collision, if you will, as the feet hit the raft. So the child then walks on the raft with a net velocity of 0.71 meters per second east relative to the water. Fluid friction between the raft and the water is negligible. Determine the resultant velocity of the raft relative to the water. So they want to know what happens to the raft, what is its velocity as the child starts to walk. So right here is before the child starts to walk, and then right here is the child walking on the raft. So what have they drawn here? Well, they've drawn this vector right here, which they're calling momentum of the system afterwards, meaning the momentum of the system as the child starts to walk. It has to equal the momentum of the system before the child is starting to walk. And they calculated that, and I hope you read about that. All right. Now, what they're basically saying is here is momentum before the child walks of the system is equal to momentum of the system as the child is walking, the after. I don't really use system. I just use P equals P prime, meaning the total before and the total after. They've decided to use system, so we'll go along with it. And here is a vector that represents, so I've drawn it right here, the momentum before and after the walking. They've drawn it right here, the momentum before and after the walking. I've drawn it right here. They're equal to each other, the momentum before and after the walking. So I'm going to draw that. And then I'm going to write this equation right here, that the momentum total, the system, momentum with the walking, right, PS prime, has to equal the momentum of the child as the child is walking, PC prime, plus the momentum of the rafter as the child is walking, PR prime. So I've already drawn the red vector here, momentum of the system prime. I'm going to draw the child's momentum as they're walking. It's totally to the east, all right? And I'm going to join their tails. And the reason I'm going to join their tails is I know that this vector here, PC prime, plus an unknown vector that I can only label, give it a name, I don't know what it is. So PC prime in black here plus PR prime, the momentum of the raft as the child is walking. If I align them up in vector tip-to-tail addition, I'm replicating this equation right here as a diagram. Look, PC prime plus PR prime. Momentum of the child as the child is walking, momentum of the raft as the child is walking. These two added together, the black plus the green, is a vector tip-to-tail addition of this equation, and they have to equal the total momentum as the child is walking, which is also equal to the total momentum before the child was walking because it is conserved. What have they drawn here? Well, they've drawn here that we've got momentum of the collision, of the system after the collision, minus momentum of the child as the child is walking, has to equal momentum of the raft as the child is walking. So they've drawn a vector tip-to-tail diagram of this equation rearranged. Let me show you what they've drawn here. They've drawn momentum of the system, right, as the child is walking, plus vector tip-to-tail addition of the negative of momentum of the child after the collision is equal to the momentum of the raft after the collision. So all they've done is they've taken momentum of the child as the child is walking and brought it over to the other side. That's all they've done here to draw this diagram. So if you add the negative of the vector, it's the same as subtracting it. And here it is. Momentum of the system plus the negative of momentum of the child, right, as the child is walking, has to equal momentum of the raft as the child is walking. So this diagram and this diagram are saying the same thing. They've just rearranged the equation. I've rearranged the equation. Well, if I rearrange the equation, I have to rearrange the diagram. That's all they're saying. And this is just a textbook version of what I just said. Figure 2A, the first figure before the walking, shows there's no net force acting on the system. Momentum is conserved. So momentum of the system before the walking equals momentum of the system after the walking. They use system, as I said. It just means total, or what I just like to call momentum. So where the subscript S represents the system. Finding the initial momentum of the system, well, that's pretty straightforward. Finding the initial momentum, which is represented by this vector right here, is just the mass of the child and the raft. Multiply it by their common velocity, and there you have it. Momentum of the system before the child starts to walk. The final momentum of the system is equal to the vector addition of the child, indicated by the subscript C, and the raft, indicated by the subscript R. So they're saying that momentum of the system during the walk is equal to momentum of the child during the walk plus momentum of the raft during the walk. Now remember, momentum of the system during the walk is just the total momentum, or what I call total momentum afterwards. So don't let that confuse you. So remember, um, we've got to use this equation here to find out how the raft responds. So luckily, they've given us information about the child's walk. And the child walks completely to the east. I've drawn it here as a representation. So we know the mass of the child. We know the child walks to the east. So we know the momentum of the child as it's walking. There you have it. Just multiply them together. There you have it. Here, we use the law of conservation of momentum, knowing that the momentum of the uh, raft and child, the system, during the walk, right, has to equal the momentum of the raft and the child, the system, before the walk. And I can write that out as an equation right here. There you have it. Because the momentum of the system while walking has to equal the momentum of the raft while the child is walking plus the momentum of the child as the child is walking. They have to be the sum. What do they do now? They rearrange the equation. I talked about this a few moments ago. And what they do is they bring momentum of the child during walking to the other side, and we're left with this equation right here. All we did is bring the PC prime over to the other side. And now they're saying, well, subtracting a vector is the same as adding the negative of that vector. That's all they're saying here. If you subtract a vector, it's the same as adding the negative. And the reason they're setting up addition is they want to get a diagram going so they can do vector, tip, to tail addition. That's why they've done this little mathematical trick here. And then it says figure 2b shows the vector subtraction using the law of Pythagoras, or what we call vector tip to tail addition. So what they're saying is, let's go back to the diagram. Let's go back to the diagram. Is I know the system momentum that is conserved. I know the child's momentum while the child is walking. I can use vector tip to tail addition to find the hypotenuse here, which would be the momentum of the raft after or during the child's walk, the prime. Now, I know that this is a right angle triangle, so I can use Pythagoras to find this hypotenuse, and I can use trig to find the angle theta, and that's what they're going to do. Let's scroll down here. Here we go. So they use Pythagoras, they use tan inverse, and we have found the direction of the raft as the child is walking. All right, it's at 17 degrees, and we have found the momentum of the raft as the child is walking, 93 kilogram meters per second. And the last thing they want us to do is say, look, if you know the momentum and you know the equation for momentum, divide the momentum by the mass of the raft, and you will have the velocity of the raft as the child is walking. And there we have it right there. So the textbook decided to use the uh, trigonometry, geometry way of solving two-dimensional collisions. All right, that's their version of it. What I'm going to show you next is how to solve this problem by using the component method. So you can compare and see what you like and what the strengths and weaknesses are of each method for this particular question. All right, so the component method. So let's establish a few things here. East is x hat, north is y hat. Let's find the momentum before the child starts to walk. So the child has a certain mass and is moving with this velocity. So here's the momentum of the child before the child starts to walk. It's all in the y hat. And here is the momentum of the raft before the child starts to walk. It's all in the y hat, right? The reason they're both in the y hat is the child is just standing on the raft, and together the child and the raft are moving in the y hat or north direction. So we add these two together as the equation says, and here is the momentum before the child starts to walk. Afterwards, the child is now walking. The child is now walking. So PC prime is equal to the mass of the child times the velocity of the child as the child is walking. And luckily, we're told what that is, the velocity of the child as the child is walking. 0.71 meters per second east. So I'm going to multiply these together, realize that east is positive x hat, and this product represents the momentum of the child as the child is walking. There you have it, 26.98 kilogram meters per second x hat. But since the child is walking, the raft also starts to respond. Momentum has to be conserved. We're not given all the information here. Okay, we do know that the mass of the raft is 43 kilograms, but I don't know what the x component of the raft's velocity will be as the child is walking. But I'm going to give it a name. Velocity of the raft as the child is walking, the prime, x hat. Velocity of the raft as the child is walking, prime, the y component. I don't know what they are, but I'm going to give them a symbol. And then I do some distributive multiplication, multiply that in. What I do know is that momentum has to be conserved. So momentum before the walking has to equal momentum during the walking. And luckily, we already did all that work up here to start substituting in. So here is momentum of the entire system, the total momentum before, and it's all y hat. We just did the calculation for that. There it is beforehand. Now, momentum as the child is walking has to equal the momentum of the child as the child is walking. So here it is. This is momentum of the child as the child is walking, plus momentum of the raft as the child is walking. So I plug that in there. And look, I've got two unknowns here. Velocity of the raft as the child is walking, x component. Velocity of the raft as the child is walking, y component. Well, if there's two unknowns, I better hope I'm going to have two equations, and I do have two equations. One of the equations is based on solely looking at x component. So look, 0, 0 equals this x component, put it down, plus this x component, put it down. Look, I have one unknown, and I can work through and solve it. And then I do the same thing with y component. Look, y component before the walking has to equal this y component, bring it down, plus this y component, bring it down, and then I can work through with the algebra and solve for it. And that's what I've done right here. I've worked through this and I've solved for it. And I have found the velocity of the rafts as the child is walking, x component, there it is, I found it. And velocity of the raft as the child is walking, y component, there it is, found it. And now I can bring it into a nice ordered pair. Here's the velocity of the raft as the child is walking, prime. I just bring the components together. Now, if you want to rewrite this in angle magnitude form, I can do that. I draw my diagram. Here's the x component. Here's the y component. So here is a visualization, a diagram of vector tip-to-tail addition. And here is the magnitude of the velocity of the raft as the child is walking, because I've added the green and the purple vectors right there. And I can find this value through Pythagoras. It's a right angle triangle, right? So if this is a right angle triangle, using Pythagoras will quickly give us 2.2 meters per second. I can find theta by using tan inverse. I know the opposite. The opposite is the y component in purple. I know the adjacent. The adjacent is the x component in green. I do tan inverse. I get 73 degrees. And now I have the velocity of the raft as the child is walking in angle magnitude form. And you'll see that this matches the solution in the textbook. All right, we're now going to look at the next sample problem in the textbook. It's on page 256, 257. So take a look at the question, look at the solution. So pause this video and really spend some time on it. Take a look at the question, take a look at the solution, and then come back to the video and we'll have a nice discussion about it. So here we go. In a game of marbles, a collision occurs between two marbles of equal mass. Very important. Mass is the same. One marble is initially at rest. There it is. It's the red marble, marble 2. After the collision, the marble acquires a velocity of 1.1 meters per second at an angle of 40 degrees from the original direction of the motion of the other marble. So this takes off at 40 degrees to this original direction right here. It's shown in the dashed line there, right here. This marble number 2 takes off at 40 degrees to this original direction, which has a speed of 1.36 meters per second after the collision. So this marble right here takes off with a speed of 1.36 meters per second after the collision. What do we want to find out? We want to find out the initial speed of the moving marble. Here it is. See how it's got a question mark here? Velocity 1 x component equals question mark. The reason they wrote x component is this is totally moving in the x direction. So if you take a look at this, the momentum of this entire system, the two of them, before the collision, the only place you're going to get momentum is from marble number 1. And there's no momentum in the y direction here. All of the momentum before the collision is in the x direction. And I've added a little note here saying, look, momentum, the total momentum before the collision, I'm just going to call it P. The total momentum before the collision is equal to the mass of marble 1, which is just m, they both have the same mass, times the velocity of marble 1 before the collision. That right there is an equation representing the total momentum before the collision. So what I've done for us here is I've used the gizmo called two-dimensional collisions, and I've tried to approximate the question as close as I could to what was talked about in the textbook. I've tried to change the numbers as close as I possibly could. So here is the blue marble. It's going to come through and hit the red marble here, or yellow in this case, orange, what have you. And notice that it's not a head-on collision. If this was a head-on collision, we would have a one-dimensional problem. This hits the other ball at an angle. It's what we call a glancing blow, a glancing hit, a glancing collision. It's not head-on, all right? And we notice that the gold marble, I guess they call it, look, no velocity, what to speak of, all right? Nothing. The blue one here, look, it's got some velocity, but it's all I hat or x hat, nothing in the y. So the total momentum before the collision comes all from the blue ball, and it's all in the x direction. So before I run through this, and you can have a lot of fun with this, just go on to the gizmo, play around with it, see what happens. You can change the mass, you can change velocities, have some fun with it. But we're going to use this just to do what the question has. All right, just to do what the question has. So I'm going to run through. Now make a prediction as to what's going to happen, and then let's do it. Now you notice one of the balls has a y or a j component to their velocity that's upward, and the other ball has a y or j component to their velocity that is downward. You can never have both balls going up or both balls going down, because you must remember that the momentum in the y direction before the collision was zero. So the momentum y component after the collision must also be zero. So you've got to have some y velocity, y momentum that's positive, and you've got to have some y velocity, y momentum that's negative, so that when you add the two of them together, you guessed it, it has to add up to zero, because you had no momentum in this system in the y direction before the collision. One has to go up, one has to go down. If you don't have that, you're violating the law of conservation of momentum. So what do we have here? Well, we've got a diagram showing the second ball going upward and the first ball going downward. So let's take a look at the second ball. We know that it takes off at 40 degrees, 40 degrees to the original direction. So there's the 40 degrees. And we know that it's moving with the speed of 1.1 meters per second. There it is. There's that 1.1 meters per second. That's the magnitude of this velocity vector. And we know that this velocity vector, the momentum vectors, can be broken down into two components, the x component and the y component. Now they talk about velocities here. I'm going to talk about momentums and tell you that the momentum of the second object, the second marble, after the collision is equal to an ordered pair, which represents the x component of this momentum after the collision and the y component of this momentum after the collision for object 2. We know the mass is m. So remember, momentum is mass times velocity. So I put an m here, put an m here. We know it's both positive x hat, positive y hat. So I got a positive here and a positive there. We know the velocity magnitude is 1.1, 1.1, so I put it on each side. But now I want to get the components. So the x component is adjacent, so I multiply that by cos 40. The y component is opposite, so I multiply that by sine. And there you have it. There you have it right there. Similarly, I can do the same thing with the blue marble, marble 1. I know it has a speed of 1.36 meters per second, so that's the magnitude of this here. It would be the hypotenuse of this triangle, all right? And I can break down this velocity into x component and y components, but I don't know the angle. So they use the Greek letter phi. That's phi. Now they use velocities here. I'd rather start out with momentum. So we know that the momentum of the first object after the collision is equal to the components of that. Momentum is equal to mass times the velocity. Well, I know the magnitude of the velocity, and I want to find the x component. The x component is adjacent to the angle phi, so I have to use cos. And it's in a positive direction, so I put a plus sign there. The y component, I still need the mass, momentum is in there, but the y component is negative. So I put a negative sign there. I still use the speed here, 1.36 meters per second, but the y component is opposite to the phi, so I use sine theta. There you have it. So next, they're saying, look, you've got to follow the law of conservation momentum. There it is. P before the collision, momentum before the collision is equal to P prime momentum after the collision, which they then break down into momentum of the first object before the collision, momentum of the second object before the collision. You have to add them. And similarly, momentum of the first object after the collision plus momentum of the second object after the collision, and you have to add them. You have to add these to get the total. Now they say, let's make life simple. We know that the masses are the same. And we know that the velocity of the second ball before the collision was 0. So they can reduce this to this equation right there. And then what they're saying in this long worded thing here is, let's break this down into components. If it's equal for the entire component, if momentum in its entirety is conserved, then momentum in the x component is conserved and momentum in the y component is conserved. So that's what they're going to do here. They break it down into y and x. Y, I've got this red arrow to show you, look, let's just take a look at the y component. And we have all of the values described to us right here. These values came from the work we did before. And we can rearrange this, and all of a sudden we have what the angle is right there. So by using the y component equation, we were able to find the angle. And all of these expressions are found on the page. We just went through it. Then they say, let's use the x component. So we use the x component of conserving momentum. But now we know what phi is. We just calculated it, so we can plug it in there, right? All of these expressions we got from further up on the page. We just finished talking about them. And now we know the speed of the first marble before the collision, right there. So this is definitely using the component method to solve this. What we're now going to do is take a look at the uh, trigonometry, geometry way of solving. I'm going to provide that solution for you right now. So here we go. I'm going to show you how to do this with trig and geometry and diagrams and such. What do we know? What's our given? What's up, G? Well, we know that the masses are equal. So M1 equals M2 is equal to M. And I've color-coded everything for the blue marble and the red marble. We don't know the speed, velocity of the blue marble before the collision. We know that after the collision, the before the collision, the second marble, the red one, was not moving, so v2 equals 0. And after the collision, we know the velocity of the second marble, 1.1 meters per second at 40 degrees to the original direction of the blue marble. And we know that after the collision, the blue marble has a speed of 1.36 meters per second, but we don't know at what angle. We have no idea at what angle. Well, how are we going to solve this problem? Well, we're going to use the law of conservation of momentum. Momentum before the collision, P, is equal to momentum after the collision, P prime. Let's draw a representation, so we're going to start a diagram here, of the momentum before the collision. And here it is. The blue arrow represents the momentum before the collision. Now, let's draw a diagram, vector signs, a representation, a graphical representation of momentum after the collision. Here it is. I'm drawing the red arrow. It's at 40 degrees to that original direction. And I know that this represents the momentum of the red marble, marble 2, after the collision, which is M2 V2 prime. There's a graphical representation of it right there. And here is a graphical representation of what is happening to the blue marble, marble 1, after the collision. It's going downward at an angle theta. We don't know what it is. There you have it. This right here, the diagram that I've drawn right here, is telling us that this arrow right here has to equal the sum of these arrows. That's what I've drawn here in the equation. P1 before the collision plus P2 before the collision. The momentum before the collision has to equal the momentum after the collision, which is P1 prime plus P2 prime. So I need to find a way to add the blue vector and the red vector and make them equal to the original vector. Well, kids, the only way I know how to add these vectors in a diagram is vector tip to tail addition. And that's what I've done here. I said, look, if you take P1, there, I've drawn P1, and you do vector tip to tail addition and add the red vector, there it is. So I'm adding the blue vector and the red vector through vector tip to tail addition. I've drawn it right there. Okay. Then I know, I know that they have to equal this vector right here, momentum before the collision. So there's my vector tip-to-tail addition. And this diagram is a graphical representation of momentum being conserved. I can write P is equal to P prime, or I can write this diagram down. They mean the same thing. So let's take a closer look at this diagram. Here is momentum before the collision. P1 is equal to M1 V1. All right. And let's just take a look at the magnitude of it. So the magnitude of P1 would equal M, because all the masses are the same, times the magnitude of V1. Here is P1 after the collision. It goes down at some unknown angle theta, right there, some unknown angle theta. So we have P1 prime is equal to M1 times V1 prime. Now let's just take a look at the magnitude of it. The magnitude of P1 prime is equal to M, the mass, times 1.36 meters per second. We were given that quantity. Now let's take a look at P2 prime. There it is, right there. I know that this is 40 degrees in here, and by the Z rule, it would be 40 degrees right in there. Now let's just take a look at the magnitude of this. So we would have the magnitude of P2 prime is equal to the mass times 1.1 meters per second. Now we're going to use sine law. Sine law. All right. So we know that this side right here, magnitude of P1 prime, m times 1.36 meters per second, this side divided by the sine of 40 degrees, because it's that 40 degrees is opposite to it. By sine law, it has to equal this side, magnitude of P2 prime, which you know is m times 1.1 meters per second. We know this side divided by the sine of theta, because that angle is opposite to that side. All right, so I can set up sine law here. I've set up sine law right there. So I set it up, I do some math, and what I do is I bring sine theta up here. I bring sine 40 degrees over to here, and then I divide both sides by 1 m times 1.36 meters per second. So I've done some algebra here. I'll take some time to see what I've done here. Take some time to see what I've done here. And basically it's cross multiplication in order to solve for sine theta. Then I divide the m's out. I do my math with my calculator and I get theta to be 31.3 degrees. So that's a really important thing for us because now I know that theta is 31.3 degrees. Well, I know that theta plus 40 degrees plus phi, which I'm going to call this bottom angle right here, let's call it phi. All three of them together has to equal 180 degrees. That's the rule for the angles in a triangle. They always add up to 180. So if I do some math here, I can find out that phi is 108.7 degrees. Right there, 108.7 degrees. I can use that and apply sine law again. But now I'm applying sine law to this side here, the original momentum, right? There it is. And its magnitude is m times the magnitude of the initial velocity. So there it is. Okay. I'm going to divide it by sine of 108.7 degrees because this angle and that side are opposite to each other. That's how sine law work. And it has to equal this side, m 1.36 meters per second, divided by the 40 degrees, which is opposite to it. There you have it, 40 degrees. So I've set up sine law. So I've set up sine law there. I notice that the m's cancel. And then I do a little bit of rearranging. I bring the sine 108.7 up to here, and I can solve for the velocity of that blue ball, the speed of that blue ball before the collision 2 meters per second. And it's the same answer when the textbook used the component method. But this is the trig geometry method. Maybe you like this way better, maybe you don't. Some questions are easier to solve with trig and geometry. Some questions are easier to solve with components. Really doesn't matter as long as we achieve the solution. So a long lesson today. We're at 40 minutes. Look at this. Okay, so take your time through this. If you have to rewind it and slow down and slowly work your way through it, please do that. Okay, we have to be patient with ourselves and really let the stuff sink in. All right, so I will post some homework questions. Have a great day. Stay safe. Bye bye.